Okay, welcome to the sixth part about functional mockup interface in industry. This time we'll talk about implementing an FMU manually. So we'll go into the details here a bit. Don't be too surprised if you see some code here. Let's get there. We want to implement a simulation model, and what we are doing here is just a prototype. It's a rather simple model that we want to implement, and it's for educational purposes. It's simplified as much as possible, and by far not all features of FMI are used. I just want to show you basic principle there. You might want or might not want to adopt to your use case. It's more that you understand how FMI works in general. What is this example model about? We call it SV on delay, switch on delay. It has one input, one output, and 3 parameters. What we want it should be a switch on delay. That means we have a Boolean comparing. We have an input, and we have a parameter U threshold, and we have an output, which is one of two values, either y0 or y1. And once the Boolean comparison has a positive edge, that means our actual input u is larger than the threshold, then we want to see a delayed positive output of y1. But as soon as we get u below u threshold, it should immediately get a negative edge also to y0. So it's like maybe you think of it in a staircase or so, where you turn it on and it keeps a bit until it's turning off, but here in the reverse. So it's like a motor, maybe better. You click it on and it starts to work, and then if you click it off, it should be directly off. And we want to implement that as FMU. It's more a toy model, as I already mentioned, so it's typically used in automation. Actually, the switch on delay for small helping functions, but here it's just for educational purposes. We have a manifest included. This image on the left side is extracted from FMI standard, and what this manifest actually says, okay, we have a FMI, it's FMI 3. So let's look here. We have FMI 3. It's called this FMI model is called SV on delay. You will have seen that eventually earlier already. Then there is this instantiation token. This just tells if there is a discrepancy between the implementation and this manifest, then we have a problem. And because there were some inconsistencies in the past, this token was introduced. So the simulation environment will check if the simulation implementation actually has the same token stored as in the XML file is stored, and if not, will reject executing the FMU. Then the next thing is we are in a co-simulation environment. We could have FMUs that are both co-simulation and model exchange. That is possible in general. Then you would have additional to this co-simulation entry, you would have a model exchange entry, but for here we have only co-simulation. Again, it's the identifier SV on delay, which is necessary at that point. Then we have here some can get and set FMU state, can serialize FMU state, can handle variable communication, provides intermediate updates, can return, and so on and so on. These are these capabilities I already mentioned. What this FMU can do. This FMU is bound to the absolute minimum, so it cannot do much, but you could enable them, and then the environment, the simulation environment, could decide to use that, but is not required to. And here's also a fixed internal step size defined, which means that this is a suggestion for the outer environment about which step size to use. It's not a requirement in the sense that it must use this. Due to numerical issues, this is not possible at all to enforce this, but in general it's a rough estimation. And then we have model variables and model structure down here. They are a bit larger in these structures. Therefore, we look at them in detail. First, definition of variables. So this is this model variables part. And here we have one example value, one variable, which is a float variable. So it's a floating point number. It has a name out low. This name is just for convenience. So we don't need this inside the implementation. This is just for the simulation environment to have some useful name. There is also this description, the low value of the output, which is also only for the human being. So it's not important for the implementation, but it's useful if you want to do it. But for implementation, what's really important is this value reference. This is an integer, non-negative, sorry. So it could be a natural number that you give. This is, in fact, the reference that is used inside implementation and also inside the manifest to reference to this variable. So you have to take each variable uniquely an individual value reference. You must not have two variables with the same value reference. This will break or will bring you in hell, more or less. And then you have, we already mentioned that, this causality, variability, and start value. So what we have here is a parameter that is fixed, means that it is going to be set on instantiated mode to the value 0, like here mentioned, but as it's a parameter, the outer simulation environment could set it to something different. This start is just the default value. And likewise, all variables of this one input, one output, and 3 parameters, I think it was, must be defined here. So we have additionally the time as independent variable of continuous system. We have the 3 parameters. Parameter is the threshold. Your threshold is variable 1. The counter max is variable 2. And there are 4 parameters. Out low and out high are y0 and y1. And these are the value reference 3 and 4. All these are fixed parameters because you can define them in the simulation environment and all is fine. Then you have the value x, which is just internal, so it's local. It's a discrete updatable value, and we start at 0. And this time it's also an integer, so it's fixed without floating point. And we have the in and the out, so this is y and this is u, and then all variables are defined as in this case discrete inputs and outputs with start for the output, start for the input, sorry. The output is calculated on the fly, so it must not define the start value, only the input. If there was no input attached to this value, then the start value would be in place. So with these XML definitions, the variables of the model are clear to the simulation environment. Now we have this model structure. Here the variable reference I wrote, as I mentioned in the slide earlier, just for simpler understanding, it's just 0 based this vector. So t is 0, uThresh 1, CMax 2, and so on and so on. It's not necessary that you do this zero based. You could put the arbitrary, more or less arbitrary value references, so they could be non-contiguous or something like this. This is fine. Just you have to stick with it. But for here, for the example, it's zero based, so that you can easily think of it. And now this model structure has two things that must be there. One is you have to declare all outputs once more. So you have to say, okay, I have an output, and this is in fact number 6. So this is 0, 1, 2, 3, 4, 5, 6. Why? Okay. And I can optionally define dependencies. If I don't define dependencies, it's assumed it depends on everything. I can also say, okay, it depends only on 2 and 5, so it is on CMax dependent, and on 3, 4, 5, so it's CMax and X. Yeah, okay, that might make sense. Why? Because what we are actually doing is we have a counter, this X, that will count up once we see a positive edge on the input, and if we reach a certain threshold, then the time has passed and we set the output accordingly. This is rather easy. And then we have also the initial unknowns here, which tells us, okay, which values we do not know at the beginning, and this is only one. This is this U. Am I correct? So 1, 2, 3, 4, 5, 6, 7. Yes. No. So 1, 2, 3, 4, 5, 6. So Y. Sorry. Yeah. The Y is unknown because as it's an output, it must be calculated, and therefore it's initially unknown. That's the point. It doesn't make sense to make a U initially unknown, because this is has a start value. Initial unknown has no start value. The FMI header files are available depending on your version. You have to choose the right ones. They are in BSD2, as far as I know, all. And for FMI3, it's about 75 basic functions that you must all implement. If you don't implement any of them, even if you don't use them, you can just put empty content there if you don't use them. But otherwise the FMI DLL will not be able to be loaded. So you have to implement all functions that the FMI standard defines in order to be able to use this FMI prototype. And to help with that, I created some sort of framework that serves as a glue code, more or less. What it does, it just implements some basic steps, more or less, and hands over to a C++ model, which is a bit more convenient to use because you don't have to handle the memory allocation yourself anymore. The C++ implements just a class. C++ defines a header and a implementation part, and the header itself is rather simple. We have the import stuff for all kind of header, blah blah. We have to use, well, also for convenience, it's useful to define the names of the variables depending on how you name them, and map them to these value references. So it makes sense to have their static mapping, so you can read it easy or more easily. Oops. And we actually have to define the model class, where some variables are necessary and others can be added on, as needed, so to call. Let's look how this could look in reality. So you have the protection, the header protection, more or less. You include the FMI types. This is this BSD kind of header that we can use. Then here this enum is just a mapping, as I said, to address these value references. So you remember time was 0, use threshold was a value reference 1, and so on and so on. And by using this scheme, you can now use threshold as an alias for the one or for the correct value reference. It's much more convenient. And then we have the actual class, the simulation class. This has a constructor. The constructor needs some FMI stuff because during construction some logging and some other stuff is going to be handed over. This will be saved in corresponding values within the class. We don't use them actually, but we prepare them so we could enable logging. Then we need a function to reset the complete FMU. We need a function to get the output. We only have one output, so this is clear which output we are talking about. And we need something to increase the time. And the time here in FMI is increased in steps, so we define the step size h, and additionally we define a new time. This is just so more or less you could go only with h, but this new time might help when you want to avoid numerical issues. This is just a try to get a bit less numerical problems there. And then we have down here some values like current time, last time, time shift. This last time stuff is about overflowing of integer values, so you can more or less ignore this last no, not last time, there's later on, there's this time shift, is it? This is about the overflow of integers, so just ignore that. We have the current time and the last time that the FMU was running. This is just to check if the threshold has in the meantime long enough been superseded. We have the actual values, the parameters. So we have the input threshold, we have the counter max, and input output, the output low and high values. These are the parameters that we defined. We have the actual state, and we have the actual input. So what you actually have inside this model, inside this class, you have all variables available at some way, like the time, the parameters, the state, and the input. Only the output is not explicitly there because it's implemented as a function, but could also be there. It's fine. Now implementation means we have to fill in these methods with life, and maybe we define some sane defaults. And what's important there, these sane defaults must be in accordance with the manifest. So if the manifest defines that a certain parameter is starting at 1, for example, your implementation must also set this to 1. You are not allowed to just assume the simulation environment will set it, I'm sure. No, it will not. If the simulation environment detects it's the same value as expected, then it will not set it. So you have actually to keep them in sync. And then we have the actual code to execute. Let's look at it. Okay, we include the header file. We need the mathematical library. And here I define some defaults as said in the manifest. This is just so that we have no static magic numbers somewhere flying around. The switch on delay constructor itself just stores these provided values in the fields of the class and sets sane defaults, as I said, for all parameters, inputs, and stuff inside the class. The reset function is called either if the class is started once. It's called at the beginning when the initialization phase is exited, I think. I'm not sure. It's on leaving or on entering, depending a bit on the implementation of the outside. But in fact, this is for starting the working phase, more or less. This is just a startup procedure. And then we have the get outputs. This is just the question: if the counter has already reached the maximum counter value, then it's out high, otherwise it's out low. So these are just the values that we get. Here we come into the increase time function. If the input is smaller than the threshold, the counter is 0 for all time. It's all fine. We don't have to think about it. If the input is above the threshold, we are in this else case. The counter could be smaller than the maximum counter value. In this case, we start increasing the counter, and the time shift here you can just assume to be 0. It's just to do the calculation a bit more exact, but in fact it's just increasing the counter by the amount of time multiplied with a factor. So if a certain time has passed, one click is going to be the counter is increased by one click, and once a certain bound is reached, then the output will be set according to whatever. And what we add here at the end is we add a check. If the counter has reached already the maximum counter value, then we bound it from above, so it's not counting into the infinity but just to the maximum counter. And then in the end we have just this current time gleich new time, which means we store our time so that we know how late it is, more or less. Okay, now you have seen a bit of implementation. It's a very simple model, to be honest, because we only used inputs, outputs, and discrete states in co-simulation, which is the very basic principle, but nevertheless you get the idea. And starting from here you can rather easily take the FMI standard, look at it, and extend to your needs this framework or this approach to get there and create your own FMUs. I hope this helped you, and I will continue with the next FMU topic about FMU and industry. Hope you continue listening to me, and see you soon. Thanks for watching.